Section 9.1, Properties of Radicals, Part 1. 9.1 is actually kind of a lengthy section, so we're going to be splitting it up into a couple of different parts. The first part we're going to be looking at simplifying radicals, radical expressions. We've already seen expressions with square roots and cube roots. Any radical expression is an expression that contains a radical, which is this symbol here. You can see we've got three examples down below. Not necessarily an equation, but just an expression that contains its square root symbol, but again, we could do this with cube roots, fourth roots, fifth roots, whatever we really want. Anyways, if we're dealing with any nth root, there are three requirements to have something in simplest radical form. It's in simplest radical form whenever no radicands, which remember are the numbers inside the radicals, contain perfect nth powers other than 1. What that would mean is that if we're talking about square roots, we couldn't have any perfect squares as factors other than 1. If we're talking about a cube root, it couldn't be perfect third powers, etc. No radicals are allowed to contain fractions, and no radicals are allowed to appear in the denominator of the fraction. And so what you see here are three examples where we're violating each of the rules here. These three examples are not in simplest radical form. This first one, square root of 108, the reason that that's not in simplest radical form is because 108 could be written as a product of a perfect square with another number. Namely, square root of 108 could be written as 36 times 3, and that would be inside the square root. So that's not simplified because I have a perfect square inside a square root. We'll figure out later how to deal with that. So that violates rule 1. The second one violates quite obviously rule number 2. No radicals contain fractions. The entire radicand is a fraction, so that's a violation of rule 2. Although it actually also violates rule 1 because 64 there is a perfect square, and that can't be, even though it's in the denominator, in a sense it's a factor, although I guess it would actually be 1/64th is the factor, but either way that's a perfect square, and so that would violate rule 1 as well. And then the third example, we have a square root of 5 in our denominator, and the bottom line is you can't have a square root in the denominator. Now we're going to see ways, not all of them today, but these are three examples. We're going to see ways to simplify them, and that's going to be our goal. We're looking to get something in simplest radical form, and that doesn't just mean using an approximation. We're going to get exact answers that will be useful for us going forward. As I mentioned, we're going to be dealing primarily with square roots. As a result, we're going to want to know some of our perfect squares. That'll be really helpful going forward. So what I'm going to do is I've got listed here just the first 20 perfect squares. You can take a second, look through them. If you want to write them down in a notebook for easy reference, it's a good idea. If you want to pause the video and do that. Otherwise, you can always come back here, or just you can calculate these too. You know, to get 17 squared is 289. Just do 17 times 17 and work the math out, and you'll get it to 289. So there you go, just a little reference for you. One way that we can simplify radicals is by using the product property of square roots, which states that the square root of a product equals the product of the square roots of the factors. What this would look like in terms of numbers is if you have the square root of 45, you could write that as the square root of 9 times 5. And then you can split up that radical into two other radicals that are being multiplied. You take the square root of 9 and the square root of 5. Square root of 9 works out nicely to 3. Square root of 5 can't be simplified, so your final answer there would be 3 square root of 5. The 9 there is your perfect square factor that's inside a radical. That's what makes the original statement not in simplest radical form. Our final answer actually is in simplest radical form. And then you can just see a general formula down here. Square root of AB is the same thing as the square root of a times the square root of b. We're going to assume that a and b are both non-negative here, which dealing with square roots of negative numbers introduces a whole bunch of other problems that we don't want to worry about. So to look at square root of 24 here, I want to see if that's in simplest radical form, and I just have to figure out, does 24 have any perfect square factors? It does, actually. 4 is a perfect square, and that's a factor of 24. So what I'm going to do is I'm going to rewrite 24 as 4 times 6. And then looking at the square root of 4 times 6, I write that as the square root of 4 times the square root of 6. Square root of 4 can be simplified to just be 2. And then I attach the square root of 6. Now what that means is 2 times the square root of 6. 2 is a number, square root of 6 is a number, and that'll give me some decimal when I multiply it out. It won't work out nicely, but that's okay. I actually want to keep it in that exact format. I want to keep it as 2 square root of 6. So that's one example there. For negative square root of 80, what I'm going to do is I'm going to think, does 80 have any perfect square factors? And it does. There's a couple of them that I could choose. I could choose 4, but if I choose 4, I'm actually going to have to then do something later on. I'm going to pick the biggest perfect square factor of 80, which happens to be 16. So I keep my negative that's outside, and I rewrite 80 as 16 times 5. Now, once again, I just split that up into the product of 2 different square roots, and that's negative square root of 16 times square root of 5. And when I do the square root of 16, that's 4. I'm just going to multiply that by whatever I already had outside. In this case, a negative. So that's going to be negative 4 and then square root of 5. And that's my answer there. So that's kind of convenient. Now when it comes to variables, in some ways the variables actually are easier or just as easy as dealing with the numbers. The bottom line is it's helpful to split it up and just kind of worry about one piece at a time. So let's give ourselves a little bit of space here. So we'll look at the square root of 49 x to the third, and we'll look at that in 2 parts. We'll look at it as the square root of 49 times the square root of x to the third, or x cubed. Square root of 49, that works out nicely. That's just 7. And then I have the square root of x cubed. Now there's a couple of ways to look at this. But the bottom line is we know that the square root and the squared cancel each other out. And so if I think about the square root of x cubed, I'm thinking about that as x squared times x as my radicand. Splitting that up, I've got the square root of x squared times the square root of x. And the square root of x squared is just going to reduce perfectly to x, because a square root and a squared undo each other. So that's going to leave me with a 7x on the outside of my radical and a square root of x on the inside. And although it may not look like it, that's my final simplified answer. 7x square root of x. Let's try the same approach for the next one. Square root of 75 n to the 5th. That's going to be the square root of 75 times the square root of n to the 5th. And I just want to break down the square root of 75 first into a perfect square factors. I think through my list, I recognize that 25 is a perfect square factor of 75. So I get square root of 25, square root of 3. I guess I kind of skipped a step there, but I think at this point you've probably recognized that. And I'll attach my square root of n to the 5th to the end of that. And then square root of 25 is just 5. And then I attach my square root of 3. And now I just got to deal with the square root of n to the 5th. Well, just like before, I like to create a situation where I can free some of these variables from the radical by using perfect squares. And perfect squares here would be n squared. You see, to get n to the 5th, I'd have n squared times n squared times n. Well, that's 5 square root of 3. Square root of n squared is just n, so I can write that twice, and then the square root of n. Now, typically we write everything that's outside of radicals together. So I'm going to take the 5, the n, and multiply those together, which will give me 5n squared. And then I take my pieces that are left inside the radicals and multiply them together. The 3 and the n would put my radicand as 3n. And so the way to simplify square root of 75n to the 5th ends up being 5n squared times the square root of 3n. What you might notice is that whenever you have a variable on the inside of a square root, if you take the exponent of the variable and cut it in half, that's going to be your resulting exponent on the outside of the radical, the whole number part of your answer. The remainder will actually be your exponent on the variable on the inside. We'll get some practice with that, but if you notice that 3 divided by 2 would be 1 with a remainder of 1. We have a 1 as our exponent outside, that's our quotient, and the remainder of 1 is our exponent on the inside. 5 divided by 2 would be 2, which is our exponent on the outside, with the remainder of 1, which is our exponent on the inside. So that's just something we'll see more in practice. Alright, one other way that we can simplify radicals is to use the quotient property of square roots, which states that the square root of a quotient equals the quotient of the square roots of the numerator and denominator. Very similar to with multiplication, we can split up a radical expression of a division, which is often expressed as a fraction, into a fraction of 2 radicals. One of the rules for simplest radical form is that we can't have a radical that contains a fraction, and so when we split this up, we see that our denominator becomes the square root of 4, which simplifies to just 2. And so while the square root of 3/4 is not in simplest radical form, it is equivalent to the square root of 3 over 2, which is in simplest radical form. In general, you can see the general formula here. If you have the square root of a fraction, you can make it a fraction of square roots, and vice versa. And we would just have to deal with the situation, which we'll see later. We want to make sure we don't end up with a square root in our denominator, so we hope that it will work out nicely. So we have just a bunch of examples here. You can see how each one works. For the first one, the square root of 15/64, we just rewrite that as the square root of 15 over the square root of 64. And now the square root of 64 reduces to just 8. And the square root of 15 has no perfect square factors, so we actually just leave it as the square root of 15 as our numerator, and that's all we end up with for our answer there, the square root of 15 over 8. Very similar thing for the next problem. I split this up so that it's the square root of 23 over the square root of 9. And once again, my numerator contains a radical, but the square root of 23 is prime. It has no perfect square factors other than 1, so it stays as 23. And my denominator is the square root of 9, which is 3. So that's all I would need to do there. And then for the last one, once again, same story. Split it up. I've got negative square root of 17 over the square root of 100. And I just want to make sure I keep track of that negative. But I'm going to have negative square root of 17 because 17 is prime. It has no perfect square factors. All over 10. And so that's what I'm looking at there. I've got 3 different problems that can be split up pretty nicely. Let's see what we can do with some variables involved. We're going to treat it kind of the same way that we did the last types of problems. Split this up. I've got the square root of 81 over x squared. Make that the square root of 81 over the square root of x squared. And now I actually can reduce both of these. My numerator reduces just to 9, and as we saw before, the square root of x squared is just x. And so I actually don't have any radicals left at all. That just simplifies nicely. It's okay to have a variable in my denominator, just not a radical. Let's repeat this for the next one. Very similar. I think you can probably already see what the answer is going to be. So you're going to have the square root of 36 over the square root of z squared. And square root of 36 is just 6. Square root of z squared is z. And that's our final answer, 6 over z. And final example, it's just a little bit more complicated. When I split it up, I get 4x squared. The square root of that is my numerator, and the square root of 64 in my denominator. Now, my numerator actually looks like one of the old problems with multiplication. So I might want to split that up and make that the square root of 4 times the square root of x squared all over the square root of 64. And now, as it turns out, I have 3 perfect squares. The square root of 4 is 2. Square root of x squared is x. Those are both my numerator. And they're multiplied, so it's 2 times x, or 2x. And the square root of 64 is just 8 in my denominator, and that's my final answer. And so that's what you do. You just kind of separate them and simplify each piece, and make sure that you're in good shape. But oh wait, actually I just realized something. We actually aren't finished with this this last problem here. Let's draw our attention to something. I realized that this could actually be reduced further. The 2 over the 8 can be reduced to 1/4. So I actually need to leave that as 1x over 4 or just x over 4. Sorry about that. Sorry I missed that. But that's all right. So that's actually the final answer that we want to use. It's not completely accurate to say that this is totally simplified. It's simplified in terms of radicals, but it's not a simplified statement. But anyways, that's what you end up with. So hope this makes sense. All right, just one last thing I wanted to point out here. Sometimes we have a problem, we try it a certain way, or it's presented in a different way, where we can't simplify it any further. We don't have good perfect squares to work with. And so when that's the case, what we'd look to do is we'd look to simplify first by either multiplying or dividing. I mentioned before that you could take a square root of a fraction or a square root of a product and split it up. Well, you can work in the other direction. So when you have the square root of 5 times the square root of 10, and neither of those reduce, you could write that as the square root of 5 times 10, which we know is the square root of 50. Now, to simplify the square root of 50, we would want to say, are there any perfect square factors of 50? And there is, 25. So I could rewrite that as the square root of 25 times the square root of 2, which then gives me my final answer of 5 square root of 2, which you might hear some people call 5 rad 2 or 5 root 2, but it just means 5 times the square root of 2. In the next example, I get the square root of 6 over the square root of 8. And that neither of those are perfect squares, so I have this radical in my denominator, which that's problematic. But what I can do is I can actually rewrite this as 1 square root of a fraction, which may not seem to be beneficial, but if it's the square root of 6/8, that's actually a fraction that I can reduce. I can do that division a little bit, so I can reduce the fraction that's inside. And if I can do that, I should, and it'll make my problem a lot easier. 6/8 reduces to 3/4. And now I can go backwards and split this up so that it's the square root of 3 over the square root of 4. And then the square root of 4 works out nicely. Square root of 3 just stays as it is, but the square root of 4 is just 2. And so that's what I end up with. The square root of 3 over 2 is my final answer. So sometimes you're going to see these problems where you're looking to simplify the radicals, and it may be worthwhile to combine or simplify your expressions by multiplying or dividing, or at least reducing a fraction first. That'll make your simplifying later a little bit easier to do. This should be helpful going forward. We're going to get some practice with all sorts of problems so you get very comfortable with these.